Welcome to Reinvent 2020. My name is Paola Lorusso and I'm part of a great team of database specialists in Amazon Web Services. We are dedicated every day to support our customers to embrace the technologies that better respond to their requirements and help on growing their business. Today, I'm glad to have with me Chetan Karakus, Head of Quantitative and Analytical Solutions at BP, and Krishna Sikaram, Technology Lead at BP. We are going to explore how BP transitioned a large-scale mission-critical data analytic platforms from a commercial database platform to the Amazon Aurora Postgres open-source platform using Database Freedom Program in an operational, fail-safe and ISO-functional way. BP will share its experience migrating with the help of AWS Database in Freedom and Aurora engineers and lessons learned along the way. Thank you.
Thanks, Paula. My name is Chetan Karakus. I'm very pleased to be here to talk about the enterprise database transition with my colleague Krishna. I will be talking about the enterprise transition, database transition part and the key tools and technologies and some of the best practices we learned. And Krishna will talk about our market intelligence platform and migration processes. So I will start with the enterprise database transition. First of all, a few definitions. So what do we mean by enterprise database? So enterprise databases are database management systems managing large amount of data in an operationally safe way. An enterprise database transition is the process of moving from commercial expensive enterprise databases to cloud-based databases. The key insight behind such a move is the fact that you could replicate the advanced features of commercial enterprise databases with open source database systems such as Postgres and the services provided by the cloud platforms such as AWS. A great example of that is the Amazon Aurora database solutions. So in a nutshell, enterprise database transition is moving away from the expensive commercial enterprise databases to cost-effective cloud-based databases. It is the process of moving away from proprietary license-restricted database systems to open-source, license-free database management systems provided on the cloud. So what are the drivers behind enterprise database transitions? First of all, the main driver is the cost savings. So commercial enterprise database management systems are expensive. They usually charge per core. So there are potentially huge license cost savings by moving away from those systems to the license-free cloud-based systems. Secondly, doing enterprise database transition could allow you to have new architectural options. So you could re-architect your storage backends with cloud-based license-free databases without worrying about the license cost explosion implications of such designs. And finally, instead of building systems and then thinking about lifting and shifting them to the cloud, you could build data-intensive systems using the cloud-native technologies from the very beginning, and hence saving time and money in the process. Now, when we think about doing enterprise database transition and using open source database systems like Postgres, you will realize there might be some shortcomings using the vanilla open source database systems. So the cloud platform provides two categories of services or capabilities, which I call it enterprise power-up, that kind of addresses such shortcomings. In the first category is the cloud technologies. So things like high availability. So this is thanks to the inherent redundancy available in the cloud infrastructure. Auto scaling, with respect to both with respect to both storage needs and the compute needs that is possible on the cloud. And auto backups, running automated backups in a kind of a safe and predictable way, and not worrying about the backups failing. And auto partitioning is the services provided by cloud infrastructure, which helps you to avoid messy and manual sharding strategies. Now, the second category of the services are around the second category of the services, what I call it cloud services, things like availability of top-notch database engineers, providing you best practices and helping you to deal with any issues you might encounter, and availability of the well-integrated tools and processes, which helps with flattening the learning curve in your organizations and also improving the productivity of your teams. And streamline DevOps operations helps with running your database operations in a smooth way. Now, any enterprise database transition activity will require a strong buy-in from your stakeholders. But from stakeholders' point of view, they might have some concerns around both the functional aspects of such an activity, and also in terms of the operational implications of such an transition. From functionally, they might be concerned whether the things which used to work keep working, or whether there will be any new functionality. Operationally, they will be concerned about whether there's going to be any degradation in the new system, or there will be any kind of availability issues. So in order to address those things, we come up with what we call it dual assurance framework. So in this framework, we address both the functional and the operational concerns and risks which are important to the stakeholders. So in the functional assurance part of our framework, first of all, we ensure that the new system is ISO functional with respect to the old one, meaning that the new system will have the same or similar functionality as the old one. Secondly, it has to have the similar performance characteristics. So this could be like speed and latency and throughput. And thirdly, it has to have the similar system stability characteristics. So this could be easily tested by observing the same sort of SLAs provided by the old system. So the second part of our assurance framework is what we call the fail safety assurance. So this relies on the three major principles. So the first one, what I call the make before break. So this is a principle I first learned from my electrical engineer professor Yorgo Stephanopoulos in network theory there. So the idea is you build the new system first alongside the old one before even kind of thinking about switching switching off the old system to the new one. Secondly, second principle is stage rollout. So this is the idea of rolling out the changes in the new system to the production in kind of a phased stages. And the main benefit of such an approach is, first of all, you will limit any issues you might have in terms of the system disruptions in a kind of a limited scope. Secondly, you will learn from your experience any issues you encounter during those staged rollouts, and that way you can reactively you can improve the subsequent phases of your project. And finally, standby switchover. So this is the idea of keeping the existing systems on standby for a while, even when you switch over to the new system, just in case if there is any catastrophic failure, so that there won't be any business disruptions.
Thank you, Paula and Chetin. I'm Krishna Sikram, Technical Lead at BP. Today, I'll be speaking about Market Intelligence Platform a BP's market data system, its technical overview and architecture, and the database migration approach from enterprise database to PostgreDB. What is Market Intelligence Platform? Market Intelligence Platform is a strategic asset of BP to gather, store, and deliver fundamental market data to support trading decisions. Market data is accessible in one place to cross-correlate fundamental market drivers. Data collected from various sources can be enriched through internal analysis and modeling. Overall, MIP provides a reliable and consistent foundation for BP's analytics team. Let's look at the high-level architecture of the MIP application. Data acquisition services are the key component of MIP architecture with a primary responsibility of gathering data from various market sources. The data collected from various market data sources is further translated and standardized before loading the data into enterprise data warehouse. Data acquisition services are set of key Windows components which communicate via enterprise messaging bus and supported by a scheduler component. The market data that is collected in enterprise database is delivered through three different applications. An Excel add-in, which is called as a discovery application, is one of the fundamental way of consuming the market data. For the advanced users who actually have the ability to consume the data in programmatic way, a MIP API is available. The market data is also available in the source format with an internal website called MRDA, which stands for Most Recent Document Archive. Let's have a quick overview on the database. MIP database is 4.5 terabyte in size with a 6 GB of data loaded on a daily basis. MIP data is distributed across 8 different schemas based on the function and domain. A star schema is in place to support the data analytics concepts. There are closely 6,000 to 7,000 queries executed on a daily basis on the MIP database. The data collected from the various market data sources is loaded on the system on a 24/7 basis, and hence the high availability and low latency is a must requirement when it comes to the MIP data warehouse. The data is stored in partitions on a daily basis and sub-partitions from each source for the ingestion and the query performances. Hence, the MIP data warehouse is a complex database. Let's look at the migration approach. First step of the migration is assessment on the current database. Based on the current feature set like multiple schemas, materialized views, and partitions, the assessment was deemed as a complex migration. The outcome of assessment was to identify the target product, in this case it was Aurora Postgre. Once the target product was identified, the schema conversion was done using the AWS Schema Conversion tool. While 80% of the database code is generated using the Schema Conversion tool, there is a 20 to 25% of manual effort needed for converting the schema to be in line with the target database. Data migration was done using AWS Data Migration Services. A separate spoke was set up to migrate the data from source to database. A code remediation and the application code was made changes to keep up with the changes on the target database. A redesign on the partition strategy was required, as the current system has a daily partitions and sub-partition with the market data source. The partition strategy was completely redesigned for the monthly partitions to keep up with the query performance. An additional caching strategy was developed to keep up with the query performance, where the queries involved complicated aggregation functions. A lot of database tuning was done to keep up with the query performance where it needed. Like any other enterprise, several teams came together for such a huge and business critical migration. It's worth mentioning that AWS technical experts helped us from step one to the last step with their knowledge. Schema conversion. Schema conversion, as I mentioned earlier, was done using AWS Schema Conversion tool. A basic standard configuration was used with a closer look on the data types, data precision, data precision. AWS SCT was generated an assessment report which surfaced the incompatibilities between the source database and the target database. The key assessment report also gave us the indication of the time and effort needed to convert the schema. Some of the key assessment findings on the current system was the several bitmap indexes were used in the source system which were not compatible with the target system. Global temporary variables, the partitions, dynamic SQLs used across the packages and procedures were surfaced as a process as part of the assessment report. As part of the code remediation, the partition strategy was entirely redesigned to keep up with the query performance. As I said earlier, the daily partitions are converted into monthly partitions. The bitmap indexes are converted into B-tree indexes. The materialized refresh strategy had to be relooked. Several packages were converted into procedures. The security model has to be redesigned to stay in line with the new target database. The application code changes were made to keep up with the new database drivers. The dynamic SQL, which is part of some of the applications, had to be changed to make in line with the new target database. Data migration. The data migration was used using the AWS data migration services. It is worth mentioning that MIP data migration took around 24 hours, while the post-migration steps like catching up with the stats and rebuilding the indexes was another 24-hour process. A separate change data capture was set up to keep up with the changes on the source system for the duration of migration. Once the schema and data is migrated, the next step was to get the performance from the system. The performance was looked at from three different perspectives. The performance was looked from ingestion, the query, and the application performance. The performance, while either matched or better in the Aurora Postgre when compared to the current system in all the factors. It is worth mentioning that the queries where it involved aggregations with across the various partitions, the performance degradation was noticed. A separate caching strategy, as I mentioned earlier, was designed to keep up with the performance. The last one I'm going to speak about today is the production cutover. Production cutover for the MIP system is very critical, as the system is business critical. A phased approach for cutover was taken to make sure that the users do not have any outage. In the first phase, the controlled rollout was with selected users. If very few users were migrated to look at the system, After 4 weeks of successful usage of these control users, full rollout was done with the legacy system being on the standby. Finally, after 4 weeks of ELS and completion on the full rollout, the legacy system was decommissioned. Thank you, Chetan. Chetan, over to you.
Now I'm going to talk about some of the key tools and technologies we have developed in our enterprise database transition journey. So the first one is what we call the automatic load simulator, ALS. So this is a tool we created to generate realistic loads on our market intelligence platform to ensure both ensure both the ISO performance of the new system with respect to the old one, and also ensure that some functional equivalence with the old system. So for us to be able to develop a tool to generate loads in our system, we had to rely on certain characteristics of our market intelligence platform. The first one was we have a service layer in our MIP platform where we route all the services, all requests coming to the system into a unified layer where we can audit and log the service request. Second feature of our platform is there is almost one-to-one mapping between the service calls and the database queries. Some of them are static, some of them are dynamically generated. And thirdly, we have an extensive performance tracking system in our platform where we record the arrival of each query, how long its arrival time, its finish time, which API triggered the call, and which call agent and user involved in the process, and the frequency of the calls. Now, using that performance tracking data, we created ALS, basically to allows us to look at the historical logs of the performance log of our system, and then come up with a tool to generate realistic loads. And to do that, we structure our system basically on kind of a 3 layers. You know, at the top, we have a user interface where it allows user interface which allows users to configure the jobs and the load simulations, kind of monitor the executions and look at the reports. In the middle tier, we have a service layer where we kind of map the APIs to the kind of the queries we will be running on the database, and job generation functionality. And all of those sit on the execution layer, where we use the cloud infrastructure to farm out jobs to simulate the load. So this tool has been a very key technology for us to ensure the ISO performance and ISO functionality of the new system. Now, I will when we talk about simulating a load on a kind of a data-intensive system, we found out that there are 3 major approaches. The first one, what I call it complexity tuning. Here, the idea is basically by increasing the complexity of the tasks you're running, you kind of simulate the load in the system. So this is a very difficult approach to implement, because it's not always possible to change the complexity of the queries you might be running on a system in a kind of a parametric way. The second approach is what's called the intensity tuning, where you increase the frequency of the jobs arriving at any point. So this is relatively easier to implement, but it has the disadvantage of you running the same sort of jobs or queries on the system, and hence some caching effects coming into place and giving wrong performance results. And the third approach is the idea of frequency tuning, where you simulate the different loads by essentially contracting and expanding the inter-arrival times between the tasks. So this is the approach we take in our ALS tool, where we look at the performance log of our system, and we create some load distribution, and we use that to essentially kind of expand and contract the frequency intervals of the job to generate the loads. So in our system, simulation system, there are 2 major parameters or knobs where we use to kind of change the load characteristic on the system. The first one is the system load factor. So this is basically whether we want to isolate or overload or underload the system. So it kind of gives us a kind of a way to, for example, overload the system to ensure that it is kind of robust. The second parameter is what we call the intensity bundling window. This is the idea of when we were looking at our performance logs, how we're gonna group the certain number of queries that coming to the system based on a certain time window. So here, essentially, a low value means that there is a kind of a high resolution. So there's a kind of we increase the intensity, whereas when we to the bundling window is wider, that means the lower resolution and frequency in the system. The second tool we created is what we call the aggregate query caching. So during our testing, we realized there were some performance issues when we were running the aggregated queries over a longer time frame, something like over 5 years, and so compared to our benchmark system. So our solution was generating some pre-aggregated results, caching them into the database in the tables, and then making some modification on our service layer to essentially route to those tables instead of the original source tables when we fetch the results. So this was a kind of a workaround to ensure that we had the similar performance characteristics with the benchmark system. I have to say that in the new version of Aurora, we seen lesser of this problem, so you might not need this kind of solution in your system. Now I'm going to talk about some of the best practices we learned along the way while doing our enterprise database transition. So the first one is the importance of setting up a firm-wide enterprise database transition governance. So the value of this thing is you can coordinate the various type of EDT activities in your organizations through a central body, which will also be the body which will interface with the external third parties such as AWS teams. It will be a place where knowledge can be shared and best practices could be adopted, and in general, or kind of organization-wide EDT activities can be coordinated. Now, as important as to have a kind of a central firm-wide governance, it's important to implement the projects in a kind of decentralized way where you empower the individual project teams to do the actual migration and transition work, because enterprise database transition is never a kind of a straightforward lift and shift and type of activity. It will requires very specific detailed knowledge of the teams who are maintaining those systems. So it's important to empower them and give them accountability to do the actual transition work. Now, we talk about the importance of the dual assurance. That is basically very critical to get your stakeholders buy-in. So by providing dual assurance framework, implementing dual assurance framework, you pretty much make the entire transition activity risk-free. So that is very important. Now, in terms of which project to kind of tackle, my suggestion is take the most challenging project first. Why? Because that way you could use that project to deal with the various type of issues you're gonna encounter, use that opportunity to learn from those issues, and share that knowledge with the subsequent waves of EDT activities and projects. So while you're dealing with those most challenging projects, it's important that you share, you capture all the lessons learned, problem solved, practices discovered in a centralized knowledge base. So that knowledge base will live in the firm-wide EDT governance organization, and it will be essentially the kind of a place where other teams can consult whenever they encounter with issues. Last but not least is the importance of being coordinating with the AWS teams. Our experiences, they've been wonderful with addressing the issues in a kind of timely manner and solving out the technically difficult problems you may also encounter. So with that, I will pass it to Paula.
Thank you, Chetan and Krishna, for sharing your experience and lesson learned. Thank you for joining this session, and please complete the survey. We will appreciate your feedback. Thanks.